Part 5, but we already did it. We put Paris into a trig function, into a wave. All it took was 15 line segments, a long equation, a spreadsheet, and several cups of coffee. But to remind you, that was not our primary motivation. This was his video on epicycles, which are more impressive. And we are convinced that our sine waves are connected to circles, and they can get pretty fancy, but not that fancy. And the biggest issue for us, besides the animation of course, the biggest issue is that this function is just a function. Each x value spits out one and only one y value. And we're changing stuff up a little bit now. Instead of x-axis as position, it's more convenient to talk about time. But really, this changes nothing for our graph. Our function scans Paris from 0 to 500 seconds, or 0 to however many seconds, 1 pixel per second, and it spits out a height value for every time. So this change to time doesn't help us solve the problem of being a function, of letting our function curve back on itself, which it can't do. For that, we will need to plot the points in the complex plane. There it is. Let's get to it. 1, 2, 3, 4, 5. Keeping the amplitudes the same, and now each time increase is transformed into a rotation. I hope you're okay with this. Remember that our Fourier series spit out not just one Paris, but an infinite series of them, going over and over and over. This, whatever it is, this will do the same thing, only instead of being stretched out forever in a straight line again and again and again, it'll be twisted around itself. I hope you're okay with that, but we're not okay. We're out of room. So hold your breath. Donk. 6, 7, 8. Out of room again. Ready? Donk. 9, 10, 11, 12, 13, 14. Put it in the center. Okay, we have a thing, but it doesn't look like anything. Maybe a baby carriage and a lightsaber? Maybe? But it definitely doesn't look like Paris. Yet at the same time, we agree that all the information is here. It's hidden, but it's there, and it's a closed loop thing, the kind of thing we wanted, and it reminds us of something we already had way back in part 1. We had this, a very crude epicycle drawn skyline of Paris, up and down and then up and down again. So now the question, if we could go from Paris to that thing, could we unwind the other Paris? Maybe. 2, 3, 4, 5, 6. Oh no. Eek! 3 possible magnitudes. What sort of devilish skyline is that? An impossible one, and I give up. No, don't give up. In a height versus time function, that would be impossible, but that's the whole point. That's the whole reason that we switched to the complex plane. Silly? No time. Yes, there is time. Hidden time. Let's start again. 1. And a time shift. 2 is moved to the right on our height versus time graph. The second point is rotated 1/12 of a circle on our complex plane. And we went over this in great gory detail in those Apple videos. E to the I theta has that special property of being perpendicular to its derivative in the complex plane. It rotates u angle theta. 3, 4, 5, 6. Don't worry, I'm in control. I'm telling you just what to do. Just listen to me. Listen to me. I will tell you how to rotate and how to magnitude. 7. And now for point 8, I want you to rotate clockwise. Not a problem at all. Just rotations and magnitudes. We'll call this next point 8.5. See that? I said let's keep this clockwise rotation going at the same angular speed, but then we drew another point in our graph there at a half time interval. If I wanted to, I have the power here. I'm in control. If I wanted to, I could have kept the time intervals the same and changed the rotational speed, but I figured, let's just draw a point right there. Okay, point 9, counterclockwise again. Full intervals now, point 10, point 11. So my claim is that there is more information here in the complex plane. Information about magnitude versus time, Also information about rotation versus time. And notice I kept the rotation speed the same. I was just able to change the direction. Again, direction is key. Like we said in the Apple video, we can change a number, a magnitude, without making it bigger or smaller. Direction is key, but look at those magnitudes again. They change steadily in time, no big issues there, a well-behaved function, 1 magnitude per time, and with this we could get that. Start here. Magnitude and rotation information. 2, 3, 4. Reversing direction now. 5. Half step blip here, it's a little 2-step here. Blip 6, 7. You get the picture. Literally. You get the picture. See, it's a better pun this time. But what about circles? We don't care about Greek letters. We want the circles. And for that, we'll need this, the complex or the exponential Fourier series, the complex Fourier series, which should, if you look at it, should look like just a small step forward from that Fourier series that we and our spreadsheets have come to love. Euler would be happy to see E broken here into sines and cosines, and don't be alarmed that we swapped from X to T. I told you about that already. That's not a big deal. This 2L thing, well, that's just the window size. Our window size is period capital T or period size 2L, so that's not a big deal. And yes, there is a C0 term. I know you were worried about that. A bigger deal is how we let n go from negative infinity to infinity. That's interesting. And just like before, our biggest challenge is finding coefficients, which we will do in the same sort of way. And when I say that, I am lying. When I say that, I am lying. These equations, they look the same-ish, and they are very much the same, but very much, to me personally, they are very different. Meaning, I can integrate this, but I can't integrate that. That not on the complex. I want to. I should be able to. I want to. I went up into my attic and found my wife's old complex analysis textbook from college, and then I couldn't figure it out from that, so I went to my local library and requested a book. I love my library. And I've read all the equations. I've talked to Kashi about them, but I cannot, at least not yet, make intuitive sense of them to put it in a video. If you can, let me know. If you can, specifically, if you can help me get from this equation to an epicycle drawn out square step by step, I want to talk to you. Let me know how you can do that, because I'm curious. But for now, I know it's possible because I've already made this. Oh, I mean that. And to do that, we needed magnitude and rotation information. Get it? Magnitudes. This term gives magnitudes, the size of the circle. How big should these epicycles be? Talk to Cn about that. And rotation. This term gives rotation, e to the I theta, better said e to the I omega t. Now the speed stays the same for any given circle, but we've got infinite numbers of circles here, or twice infinite numbers of circles here. Add them all up and our line can move anywhere and draw anything. And notice what n does. One more thing. Notice what n does. It gives us positive and negatives. It gives us changes in direction. We wanted that. And also insists that every circle moves at an angular speed that is a whole number multiple of some fundamental frequency. Just like standing waves. Just like Paris waves. You believe me, right? One last thing before we end, and there is another video. Sigh. You've probably heard about the controversy between geocentric and heliocentric cosmologies. You may have heard that Ptolemy used epicycles and Kepler used ellipses. Ellipses fit the data better, yes, that's true. But if epicycles can build ellipses, does that mean that the complex Fourier series shows us that Ptolemy could have been right after all?